Hello, this is a video about moments, bending moments and shear forces on a simply supported beam. Now a simply supported beam is a beam that's supported by 2 points, here and here, and they can be anywhere along the beam, but in this instance they are on either end. With a beam that's supported by 2 points, think about this ruler. I've got force, the actual weight of the ruler, which is a force moving downwards, and it's supported by, in this case, my 2 fingers, but here the 2 support points. And the 2 support points need to create a reaction which reacts against the force acting downwards so that we maintain what's called static equilibrium. The other type of equilibrium is where we get turning forces which try to turn the beam this way or this way, and they also need to be equal, and they're called bending moments. And where we have the forces interacting directly with the beam, we have something called shear force. So we're going to work out all of the 3 main things here: the moments, the bending moments, and the shear forces on a simply supported beam. So the first thing we're going to do is we're going to work out the reaction L and the reaction R. Now, if we think about a turning moment, if you think about the reaction at L, we have the force at L here times the length, and to maintain balance, the moments taken from R must equal L. And we look at the length here, we've got 4 times 5 times 3 times 2, which equals 14. So 14L is equal to the first moment, which is 2 meters times 1 kilonewton, plus the second moment, which is 5 meters times 4 kilonewtons, plus the third moment, which is 10 meters plus 3. 14L is equal to 52, and when we separate the 14 from the L by dividing this side by 14, we find the reaction L at this point to be 3.71 kilonewtons. Simply then, from that we can find reaction R, because as I explained earlier, the forces acting downwards must equal the reactions acting upwards. Now we know this reaction, so we simply take all of the down forces, which are 3 plus 4 plus 1, we subtract the reaction we know, which is 3.71, and that leaves us with 4.29 kilonewtons. So that's all of the reactions for this simply supported beam worked out. The next thing to do is to find the bending moments. Now the bending moments will always work out the same either side of each point. On the end of a simply supported beam, the bending moments are equal to 0. If we work from right to left, we find the first bending moment to be the reaction at L, which is 3.71 kilonewtons here, hope you can see that, times the length here. And that gives us a bending moment of 14.86 kilonewton meters, which is shown on a bending moment diagram at this point here. And that's a positive bending moment because reaction L works upwards. Quick whiskey. The next bending moment is at point C, so I'll label this. This was point A, and at point A there is no bending moment. At point B, the bending moment is 14.86 kilonewton meters, and at point C, which is here, we take the reaction L, this time multiplied by the entire length, which is 9 times 3.71, minus this bending moment caused here, this time by the 3 kilonewtons, and because it's a minus because the 3 kilonewtons is acting downwards on the beam. And that's 5 times 3. At C, the bending moment, 3.71 times 9, is minus 5 times 3 is equal to 18.39 kilonewtons. And on a bending moment diagram, that would be marked here. And the final bending moment at D can be found by this time 12, 4, 5, 3, 12 times the reaction, 3.71, minus, this time we've got 8 times 3, and 3 times 4. So those two bending moments downwards. The longer one, which is the one between here and here, okay, 8 times 3, 8 and 3, and the shorter one, 3 and 4, or 4 and 3. Doesn't really matter. When you put them together, you're going to end up with, I think, 3.71 times 12 is 44.8, something like that, minus the other two, that's going to give you 8.57 kilonewtons. And then that comes down to here, it's marked here. And as we know, the bending moment on the end will be 0, so that will meet up there. And that concludes your bending moment diagram. Simply, from that point, we do the shear forces, which are relatively easy actually, especially on a beam that has no apparent weight. Sometimes with beams we have what's called a uniform weight for the whole beam, but this one we're neglecting that, so this is actually quite easy. The reaction at this point moves directly upwards, 3.71, and then we move all the way along to the first point of loading here, 3 kilonewtons, and that's down. So all you do is you simply draw this down, minus 3. We go along to the next point of loading here, and we draw that down a further minus 4. Along to the next point of loading, draw that down a further minus 1. And then finally, this reaction here, plus 0.429, takes us all the way back to 0. And that is all the shear forces worked out, and of course you can see how neatly it works. We have the two reactions, the forces acting downwards equal the two reactions, voila. Job done. Okay, hope that helped.